So when we discussed the examples with two variables, so there was this particular example with multiple optimal solutions. And remember, so in that case, there were two different corner points which were optimal, right? Okay? And then I think one of you asked the following question. So is it always the case that if there are multiple optimal solutions, then there's always two corner points which is optimal? So basically, suppose that I have an LP problem with, let's say, more than one optimal solution. And in that example, there were two different corner points which were optimal. Do you remember the example? So example 3, I think, was that. Question? Yes?
We always find the maximum number of corner points. I mean, two planes can intersect, but also forms a line.
Okay. Exactly. So this is the largest possible. Okay. So I can never have more than 20 corner points in such a case. Okay. So in this case, I have only 8, and 8 is obviously smaller than 20. 20 is the largest you can have. Okay. Just like we had, for example, in the previous example, not every 3 lines actually define a corner point. Not every 3 constraints or not every 3 planes define a corner point. But you need 3 planes to define a corner point. Okay. So now let me just sort of repeat my question. So basically, in 2 dimensions, so there was this example that we had actually multiple optimal solutions, and it was something like this. So suppose that this is my feasible region, and we have non-negativity. So this is my feasible region. And we said that, for example, if my isoprofit line is something like this one, parallel to this constraint right here, then everything on this line segment would be optimal, right? So, for example, everything here would be optimal. And then we said that in that particular example, there were actually 2 different corner points which are optimal, right? Okay? So the top left corner point and the top right corner point are both optimal solutions, basically, right? Okay? There are infinitely many optimal solutions, but there are 2 corner points that are optimal. Okay? And there was the following question. So is it always the case that if there are multiple optimal solutions, then there are 2 corner points which are optimal? Okay? So that's my question. So in other words, is this a typical example? Okay? In the presence of multiple optimal solutions. And I'm going to tell you that the answer is no. Okay? So in particular, let me just come back to this example. And let me change the objective function in the following way. So suppose that my objective function is trying to increase, let's say, maximize x2 only. Okay? So I'm going to replace this by, I'm going to try to maximize only my objective function x2. Okay? Now, how does my optimal solution change? Or does it change? Well, when we think about this is the following. So once again, we're going to try to draw the isoprofit plane in this case, right? So what does the x2 equals 0 plane look like? Well, this is essentially the same as the x1, x3 axis, basically, right? Okay. And what's my improving direction? Well, for the new objective function, it's going to be 0, 1, 0, basically, right? I'm just looking at the coefficients of x1, x2, and x3. So I have 0, 1, 0 for the new objective function. And 0, 1, 0 vector actually points in the upward direction, right? Okay. So as a result, I'm going to start with this plane, and I'm going to try to push it up as much as I can. Okay. What's the best I can do? Well, the best I can do is when I exactly coincide with this plane, with this top plane. Okay? Now, how many corner points are optimal in that case? Well, there are 4 of them, basically, right? Okay? Now, in general, if there are alternate or multiple optimal solutions, there can be any number of corner points that are optimal. Okay? So this example tells you that you can have 4 corner points that are optimal, you can have 5, 10, whatever. So it really depends on the example. The only thing you know is that there will always be a finite number of corner points. Okay? So as a result, if there are multiple optimal solutions, there can be any number of corner points that are optimal. So that's important. Okay. So as a result, please do not think that, for example, if there are multiple optimal solutions, then there can be only 2 corner points that are optimal. Okay. So that's the case in 2 dimensions. But if you go to 3 or higher dimensions, then you can have as many as 4, 5, whatever, any number of corner points can be optimal. Is that clear? So I just want to make sure that that's the case. So if there are alternate optimal solutions, there can be any number of corner points that are optimal. Is that clear? Is that clear? Yes. Okay, good. All right. So now I'm going to continue my discussion. So now let's go back to 2 dimensions. Now in 2 dimensions, now corner points are defined. by the intersection of two lines, as we said earlier. So, in many examples, two lines, or let's say the intersection of two lines, and corner points correspond to each other in a unique way. I'm going to explain what I mean by this. So in other words, what I'm saying is usually there's a one-to-one correspondence between each corner point and the intersection of two lines. So in other words, the number of corner points is the same as number of intersection of two lines in your feasible region. But this is not always the case. But not always. And I'm going to give you an example. So let's consider the following example. So suppose that I'm trying to maximize x1 plus x2. And my constraints are x1 is less than or equal to 1. x2 is less than or equal to 1. 2x1 plus x2 is less than or equal to 3. And x1 plus 2x2 is less than or equal to 3. Then I have non-negativity of x1 and x2. So I have a total of 6 constraints, and I have only 2 decision variables. Okay? And let's draw the feasible region. So okay, we have 2 variables, so this is easy to do. First, I'm going to start with x1 less than or equal to 1. So that's easy. So that looks like, say, this constraint right here. Similarly, x2 is less than or equal to 1. That actually looks like this constraint right here. Okay. What about this one? 2x1 plus x2 is less than or equal to 3. So if x1 is 0, x2 is equal to 3. And 3 is, let's say, somewhere over here. Okay. And if x1 is equal to, if x2 is equal to 0, x1 is equal to 3 over 2. And 3 over 2 is somewhere over here. Okay? And if I draw this line, and if you try the origin is satisfied by this line. So as a result, that's the constraint corresponding to this one. And finally, x1 plus 2x2 is less than or equal to 3. So if x1 is 0, x2 is 3 over 2, which is somewhere over here. And if x2 is 0, x1 is equal to 3, which is somewhere over here. So it goes through these 2 points. So this is the region corresponding to fourth constraint. And then finally, we have non-negativity of x1 and x2. So what's my feasible region for this problem? So it's just a square, right? Now, what is this point right here? What are the coordinates of this point? This corner point? It's 1, 1, basically, right? And if you plug in 1, 1, you're going to see that each of the constraints are satisfied with equality when you plug in 1, 1, right? So this is exactly equal to 3, this is exactly equal to 3, this is exactly equal to 1, and this is equal to 1. So which means that the point 1, 1 lies on each of these 4 lines, basically, right? So this is my point 1, 1. Now, in this case, the problem is the following. So this point lies on the intersection of 4 lines at the same time, right? Okay. But we said that corner points are defined by the intersection of 2 lines. So what's going on here? Well, essentially, but first of all, there's no problem still, so that's the good news. Okay. However, there's a sort of certain complication, and the complication is the following. So when I try to write this line, this point right here, this corner point, I know that there are 4 lines actually intersecting at the same point, and I can pick any 2 of them, okay, to write this point right here. So for example, if I take this line and this line, their intersection actually defines this point, okay? If I take this line and this line, their intersection still defines the same point, okay? So which means that in this example, there's not really a one-to-one correspondence, right? So for example, this corner point is defined by the intersection of many different pairs of lines, so to speak, okay? So as a result, despite the fact that in general, usually there's a one-to-one relationship, but there are some examples for which this is not the case, okay? So in this case, as I said, there's a one-to-one relationship for this corner point. There's a one-to-one relationship for this corner point because only these 2 lines define this corner point. However, for this point, there are actually 4 candidates, and you can pick any 2 of them. And regardless of which 2 you pick, you will always get the same corner point. Does everybody see that? Okay. So as a result, in how many different ways can I pick 2 lines in this case for this corner point? So there are 4 lines that I can pick, and I need only 2 of them. So what is 4 choose 2? Well, there are 6 different ways, basically, right? I can write. So in other words, the intersection of 6 different pairs of lines actually correspond to the same corner point in this case. Okay? Does everybody see that? Okay. So as a result, let me just write it down. So the corner point 1, 1. The corner point 1, 1. Can be written as the intersection of 2 lines in 6 different ways. Where does 6 come from? 4 choose 2, exactly. So from 4 candidate lines, I have to pick 2 of them, and I can do this in 4 choose 2 different ways, right? Okay. So as a result, basically, this is an example to illustrate that there's not always a one-to-one correspondence between every pair of lines and every corner point. So that's the main message here. So there are some examples such as this one, for which the same corner point can be written by the intersection of different pairs of lines. Okay. So as a result, there's not really always a one-to-one correspondence. And this example illustrates that. Okay. So for instance, if you look at this example, you can say the following. Well, if I simply remove this constraint, okay, and also if I remove this constraint as well, then my feasible region does not change, basically, right? Okay. So we still have the same feasible region. Okay. So as a result, this example, you may think that, well, these constraints, there's no need for this constraint and this constraint. So if I remove these constraints, then I can fix that problem, right? Okay. And the answer to that is yes. So indeed, if you remove these 2 constraints, you're not changing your problem. You're not changing your feasible region. So as a result, again, this point will be given by the intersection of only these 2 lines, and everything will be fine. So as a result, that is the case. Okay. So you can think that, okay, in such a situation, I can always remove a constraint without changing the problem, right? So at least this example sort of tries to, in some sense, illustrate that. Or, you can sort of try to conclude that that's the case, but that's not always the case, okay? First of all, this constraint, okay, as I said, does not change your feasible region, okay? Does not affect your feasible region. So such constraints are called redundant constraints, okay? They're redundant because they don't change or they don't affect your feasible region. And by removing those constraints, you're not changing your problem. So in this case, we have 2 different redundant constraints. This one is also redundant, and this one is redundant. Okay? So basically, redundant means that if I remove that constraint, then my feasible region stays the same. Okay? So it's a constraint that's satisfied automatically in some sense by my problem. Okay? So in this case, as I said, both of these 2 constraints are satisfied automatically by every feasible solution. Okay? So which means that you can really get rid of those constraints without changing your problem. Okay? However, so, and you may think that, well, if I simply remove redundant constraints, then I'm not going to have this problem at all. Okay? But that's not the case, because if you go to higher dimensions, so this situation does not always does not always arise from redundant constraints. Now think of the following example, example number 4. So now I'm going to give you an example in 3 dimensions again. And remember, in 3 dimensions, we need 3 planes, right? So intersection of 3 planes actually defines a corner point. So think of this as my first corner point. Sorry, first plane, okay? And then suppose that here there's another plane. Then over here there's another plane, and here there's another plane. So this is like a pyramid, basically, right? So how many constraints do I need for the pyramid? So the pyramid has 5 faces. So as a result, there are 5 constraints for this problem. Okay. And for instance, if I look at this corner point right here, so this is the first plane, this is the second plane, and the bottom one is the third plane, right? The intersection of 3 planes actually define this corner point, right? Okay. But how about this point right here? So how many planes intersect at that point? There are actually 4 of them, right? Okay. So those 4 planes actually happen to intersect at the same points. Okay. So as a result, despite the fact that intersection of 3 planes actually tell you or give you a corner point, in that case, actually 4 planes happen to intersect at the same place. Okay. So still, just like we did in 2 dimensions, in 3 dimensions again we still need 3 different planes. Okay. The intersection of 3 planes. However, in this case, there are 4 candidate planes from which I can choose. Okay. So I can still choose 3 out of 4. So as a result, the top point, the top corner point, can be written as the intersection of 3 planes in 4 different ways, basically, right? There are 4 planes I can choose, and I should choose 3. So 4 choose 3 is equal to 4. So as a result, the top point can be expressed as the intersection of 3 planes in 4 different ways. Okay? And unlike the previous example, none of the constraints in this case is redundant. If you remove any constraint, then your feasible region will change. Okay? So as a result, such a case does not always happen because of this situation, okay? Because of redundant constraints. So that's the main message. So as a result, the top corner point can be written as the intersection of 3 planes in 4 choose 3, which is equal to 4 different ways. So as I said, in this example, there are no redundant constraints. Okay? So as a result, such situations does not always arise from redundant constraints. So this example illustrates that. Okay. Why am I actually telling you this? Well, later on we will see that this type of situations may cause some problems. Okay. So I'm going to tell you later on what kind of problems they may sort of lead to. But we're going to see later on that such corner points have to be handled carefully in some sense. Okay. So you have to sort of be careful with such corner points, because if you're not careful, then you may run into trouble. We're going to see that later on. But essentially, I'm just illustrating that such cases can happen. So there are examples of Alper problems in which, for example, in 2 dimensions, there may be more than 2 lines intersecting at the same point. In 3 dimensions, there may be more than 3 planes intersecting at the same point, and so on and so forth. Okay? So this type of situations may arise, and we will look at this in more detail later on. Okay? For now, I just want to tell you that this type of situations can happen. Okay, so as a result, there's not always a one-to-one correspondence between the number of planes and the number of vertices. Okay, the number of corner points. Any questions? So are these 2 examples clear? So, okay, all right. So I'm going to continue with the following question. So, what is so special about corner points? Sorry, that's going to be our next question. I'm sorry. Let me continue with this one. Sorry about that. I'm going to pose that later on. Here's another question. So does every LP problem with feasible solutions have a corner point? So my question basically is that, I mean, so far all the examples we have seen, all the LP examples we have seen, actually had corner points, right? Okay. So my question is it true for every LP problem? So is it necessarily true that if I have an LP problem and if my LP problem has feasible solutions, then there will be at least one corner point? So is it necessarily true that every LP problem always has a corner point? Why?
Because we have to have a feasible region.
Okay.
In order to have a feasible region, we have some restrictions, and those restrictions has to
Intersect.
the corner point.
Region, okay. Yes?
If there is no corner points, then the problem is unbounded. I mean, there may a feasible region exist, but it should be unbounded.
Okay, so the answer is basically no or yes?
Yes.
Okay, so once again, I mean, let me repeat my question again. So my question is the following. All the LP problems we have seen so far actually had corner points, okay? All of them, including this one, the previous one, and so on and so forth. That one, that feasible region over there. So my question is the following. So is it always true? So is it always the case that an LP problem always has a corner point? Sure.
Can we have any constraint that not contains equality, just strictly less or strictly greater than?
We cannot have that because then that would not be an LP problem, right? So in an LP problem, we should have either less than or equal to, or equal to, or greater than or equal to. Those are the only options we have. Okay?
We must have equality.
We can have equality, but we cannot have, for example, strictly less than.
Okay.
Okay? Yes?
I think we should guess at this one because for to be an LP problem, the unknowns must be greater or equal to 0. So the 0.0 point must always be 0.
Okay, well, so do we always have non-negativity? So
For LP problem.
should we always have non-negativity for an LP problem? For example, suppose that I'm defining a variable x, and that shows me, for example, how much I deviate from a certain target, okay? So it can be positive or negative, basically, right? So if I define my decision variable that way, then it need not be non-negative, right? Okay? Yes? No? Do you have an example?
I have an example like that. If x, for example, x1 is less than or equal to 2 and x1 greater than or equal to 1, then between this whole region, like paralel olunca olur.
Exactly. That's exactly the example I'm looking for. So the answer is actually no. Okay? So there are examples of LP problems with no corner points. And I'm going to give you one such example. Example number 5. So suppose that I'm maximizing x1. Okay? Let's say, or x1 plus x2. Subject to x1 is less than or equal to 1. x1 is greater than or equal to 0. Okay? And suppose that I have no restrictions on x2. So x2 is free. Okay? This is a perfectly fine LP problem. Okay? So I have my objective function, my constraints. The only thing is that so there are no constraints that involve x2. Okay? In my problem. Okay? So what does a feasible region look like? So I have my x1 axis and x2 axis. So what does the first constraint look like? So x1 is less than or equal to 1, so which means that everything should be on or to the left of this line. And x1 is greater than or equal to 0, which means that everything should be on or to the right of this line. And there are no restrictions on x2. Okay. So what's the feasible region? Well, it's this region between these two parallel lines, basically, right? Now, how many corner points are there? There are no corner points, basically, for this problem, okay? Because regardless of what point you give me, I can always find two other feasible solutions such that that point will be in the midpoint, right? So, for example, if you give me any points such as this one, then I can find this one and this one. Or if you give me any points such as this one, then I can find this one and this one, and so on and so forth. So as a result, this is an example of an LP problem that contains no corner points at all. Okay? So in this LP problem, we have no corner points. So as a result, basically, not every LP problem has a corner point. Okay? However, so now if you compare this problem, this feasible region, okay, with, for example, this one right here, okay, and this one does have corner points, right? Whereas this one right here does not have any corner points. Now, what's the difference between these two? So what makes one has a corner point and the other does not? So what's the sort of main difference between these two? The first one is bounded, the second one is unbounded. That's true, but we have seen examples, for example, such as this one, for instance, right? And this is also an unbounded feasible region, but there are corner points, right? For example, these are corner points.
Has a rule and definition.
Constraints are parallel to one another. That's true. Okay. That seems to be the main problem in some sense. Since they're parallel, of course, they cannot intersect, right? And if they don't intersect, then there's no corner point. Yes.
This one not defines a good an LP problem model. I mean, for example, in this one, we can define a minimum, or a max, we can define a minimum.
Okay. But once again, I'm not really asking whether this is a good LP problem or not. Okay, so I mean, so that's an LP problem. That's a valid LP problem. Okay, and so is this one, for instance. Okay, so my question is the following: so this one has corner points, but that one does not. Okay, and what I'm trying to do is the following: I'm trying to identify a property, okay, which is satisfied by this one, but not that one, to make sure that there will be corner points. Okay? Yes?
If none of the decision variables doesn't have any freedom of definition, then we have to have a corner point.
Constraints have no common points. So in this case, we have some common points for the constraint, but in the previous one, we didn't have. So the problem is this.
So once again, I mean, you're getting close, but let me just sort of show you the right direction, okay, to think at least. Now, in this case, we have these two constraints, okay, and these two constraints are parallel, so which means that they never intersect, right, with one another. And in order to have a corner point, they should intersect, right? So, for example, in that example, we have intersection of different pairs of lines, actually, and each of them defines a corner point. So, for example, that example has 3 corner points, right? The one on the right. Whereas this one has no corner points, okay? So my question is the following. So basically now the problem seems to arise from the fact that I have 2 parallel lines that do not intersect, okay? Now my question is the following. So when can that happen? For example, here I don't have that problem, right? Okay? Now also, one thing you should be careful about is the following. It's not really a problem of having parallel lines, because I can also have a situation such as this one. So this is, again, my x1 and x2 axis, okay? And I can have a constraint that's parallel to this one, okay, for instance. Then my feasible region would be sort of this region right here, and I still have corner points, okay? So it's not really just a matter of being parallel. So there's something else going on, basically, okay? And my question is, what is that something else? So what is the property that makes that feasible region have corner points, but this one does not have corner points?
We have less constraints.
That's true.
We don't have a non-negative constraint for x2.
Okay.
First example.
Okay.
Then we'll not restrict x2 in the negative way.
Okay.
Then that creates the infinity part of the.
Now, there's one fundamental difference between this feasible region and that one, okay? There's one fundamental difference, and that fundamental difference is the following. So if I look at this feasible region, and if I draw this line, for example, okay? For example, x1 equals 1 over 2, right? So this line is contained entirely in the feasible region, right? So this feasible region actually contains this blue line, right? Okay? Whereas if I look at that example, I cannot find the line that's contained in that feasible region, right? So if you give me any line, you know, whatever that line is, then that line will always cross my feasible region, but will not be contained in the feasible region, okay? So in other words, that feasible region contains an entire line, okay? Whereas this one does not, okay? Why not? So even if you give me this line right here, then this portion of the line actually will not be contained in the feasible region. Okay? So as a result, the main difference actually between these two feasible regions is that one of them contains an entire line, okay, but the other does not. Okay? And all the examples that we have seen so far actually satisfy this property. Okay? So every feasible region, such as this one, for instance, right here. So again, this one does not contain a line either, right? So as a result, if your feasible region is such that there is a line contained in the feasible region, such as this one, then that feasible region will not have any corner points. Okay? So that's the property. That's the problem that this feasible region has, and that feasible region does not. Okay? So as a result, let me write it down. So the problem is that, so the feasible region of example 5 actually contains an entire line. Such as the blue line that I just drew. Okay? So as a result, if your feasible region happens to contain an entire line, then that feasible region cannot have any corner points. Okay? So that's the problem. Okay? And here is the sort of statement of a main result. So this is theorem number 1. So suppose that an LP problem has a non-empty feasible region. Has a non-empty feasible region. So which means that there's at least one feasible solution. Okay? Then if the feasible region does not contain an entire line, then there's at least one corner point. Now this is important. This actually gives you a characterization of LP problems that have a corner point. Okay, so essentially, if you give me an LP problem, and if I draw the feasible region, and the feasible region does not contain a line, then there will always be a corner point. Okay, And all the examples that we have seen so far actually satisfy this property. So that's why we always had corner points. So it's a good idea to actually go back and check your examples later on. But you're going to see that every LP problem that we have seen so far satisfies this property. Okay? The feasible region never ever contains a line. And if the feasible region does not contain an entire line, then there's always at least one corner point. There may be more than one, but there's always at least one. Okay? So basically, some of you actually noticed this already. So if I add the following constraint, so if I say x2 is also non-negative, right? Then all of a sudden my feasible region will change, right? So how does it change? So now I'm going to also include this portion. This also is a constraint in my problem. And now my feasible region will change, and it will boil down to this one right here, right? So now the feasible region will be basically everything on or above the x1 axis in between these two lines, okay? So now I have corner points all of a sudden, right? Okay, so I have actually two of them. Now what's the effect of adding this constraint? Well, by adding this constraint, this blue line is no more included in my feasible region. Okay? So by adding this constraint, I make sure that my new feasible region does not contain an entire line. And if you think about this a little bit, it's not too hard to see that this feasible region can never contain a complete line, basically, right? Okay? Well, so, and all the examples we have seen so far actually satisfied these conditions. So we always said x1 non-negative and x2 non-negative, right? Okay? Now here's my claim. So if my decision variables are non-negative, okay, if x1 and x2 are non-negative, then there's always a corner point. Where does that come from? Well, 0, 0 is not necessarily a corner point, because I can have a situation such as this one. So this is x1, this is x2. Then my constraint can be something like this. Okay? So then this will be my feasible region, right? So 0, 0 will not be feasible. Okay? But I still have corner points. Okay, for this problem. So my question is the following, or my claim is the following. So if all of my variables are non-negative in an LP problem, then there's always a corner point. Where does this come from? Try to think of this example. So what happened after I added x2 non-negative constraint? Well, I got rid of this portion of the feasible region, okay? And now this blue line is no more included in my feasible region, right? Okay? So what's the connection then?
I mean, every line that we draw have to intersect both horizontal or vertical axis.
Okay.
Hence, we cannot draw a line, draw a full line.
So that's basically good. Essentially, the way you should think about this is the following. So whenever my problem has the constraint that x1, x2 are both non-negative, then the feasible region will always be in this quadrant, basically, right? Okay? Now, if the feasible region is a subset of this quadrant, okay, so it should be included in this quadrant, basically, but it can be even smaller than this, okay? Then I claim that such a feasible region can never contain a line. Why not? Because if you think of any line, okay, then the line at some point will move out of this quadrant, basically, okay? So in other words, if you only look at the non-negative x1 and x2 values, then that region alone cannot contain a line. Why not? Because at some point that line will actually, leave your quadrant, basically, okay, non-negative quadrant. So as a result, as soon as you have x1, x2 non-negative, you already make sure that a line cannot be contained in your feasible region. Okay? Why not? Even if you think about the x1 axis, for example, think of this as a line. Well, it will be included up to this point, but the left of this line will not be contained in the feasible region. Okay? If you look at a line such as this one, then this portion of the line will not be contained. Okay? So as a result, as soon as you have non-negativity of your variables, you already make sure that your feasible region cannot contain a line. Okay? So that's the reason why all of our problems always had corner points, because we always had examples with non-negative variables. Okay? So let me write as a corollary. Corollary 1. Suppose that an LP problem, has a non-empty feasible region. Non-empty feasible region. If each variable is non-negative, then there's at least one corner point. So once again, I mean, the reason why this is true is that because if all the variables are non-negative, you already sort of make sure that your feasible region is restricted into this portion, okay? And in this portion, you can never have a line that's contained entirely in this portion, okay? Every line that you can draw has to leave this region at some point, okay? So which means that for every line that you give me, some portion of the line will not be contained in this feasible region, okay? So as a result, by using the first theorem, then I can guarantee that if there's no line contained in my feasible region, then there's at least one corner point, and non-negativity always ensures this. Okay, so non-negativity always makes sure that this property is always satisfied. Is that clear? So does everyone understand what it means not to contain a line? So basically, if your feasible region does not contain an entire line, then you're okay. Okay, and if you have non-negativity constraints, then your feasible region can never contain a line. Okay, and by combining these two, you make sure that if your variables are non-negative, then there's always at least one corner point. Is that clear? So any questions about these two? These are important, yes.
What if we had a line in that case, like minus x1 plus x2, very close to 1, but if and only x1 is smaller than 0. If the function is defined partially, I mean, minus x1 plus x2 greater than 1.
Okay. Okay, I'm not talking about constraints here. I'm talking about basically, I'm drawing my feasible region, and I'm asking myself, does my feasible region contain any line or not?
Yes, but it contains a line, but it has a corner point.
Okay, so what's the line again? So I have my x1, x2 axis, right? This is my x1, this is my x2. And both of them are non-negative, right?
The first two lines are the same, like x1 smaller than 1, smaller or equal to 1, and x1 is greater or equal to 0.
Okay, okay. Okay. Other questions? All right, so as a result, as soon as we add x2 non-negative to the example, as I said, all of a sudden we have corner points, okay? Because all of a sudden we're now destroying that property, the property that my feasible region, first of all, included that blue line. And by adding the constraint that x2 should be non-negative, then that blue line is no longer including my feasible region, okay? And if it's not including my feasible region, then I satisfy this property. The feasible region does not contain the entire line. So as a result, from this theorem, I deduce that there should be corner points, okay? And indeed, by adding x2 greater than or equal to 0, we do get corner points. So now I can actually pose the following question. So we know exactly when we can have corner points for an LP problem. So the question is, what is so special about them? So why do we care about corner points? So the question is, what is so special about corner points? And here is the sort of the important answer, and this is really important. So this is one of the most important sort of answers in this course. So if an LP problem has an optimal solution, so remember, there are LP problems which have no optimal solutions, right? So the problem can be infeasible, or the problem can be unbounded, right? So in such cases, there is no optimal solution, but in every other case, there is an optimal solution. So if an LP problem has an optimal solution, and if the feasible region contains a corner point, and we already know which LP problems have corner points, okay? Then the conclusion is that there's always a corner point. There is always a corner point which is optimal. Now, this is really one of the most important sort of messages in this course. Let's try to understand what it says. Suppose that I give you an LP problem, okay? And suppose that the LP problem has an optimal solution, so which means that the problem is not unbounded and the problem is not infeasible, okay? So it may have one or alternate optimal solutions, okay? Doesn't matter. If the problem has an optimal solution and if the feasible region contains a corner point, so which means that if the feasible region does not contain an entire line, essentially, okay? Then it says there's always a corner point which is optimal. What does that mean? So even if I have like multiple optimal solutions, I know that there's going to be at least one corner point which is optimal. Okay? So essentially, for instance, in this case, even if I have like multiple optimal solutions such as this one, I know that there's going to be at least one corner point which will be optimal. In this case, of course, there's going to be two of them. Okay? So what's the implication of this? Well, basically, if you look at this answer, it tells you that if you want to solve an LP problem, you may just look at corner points. So you don't need to look at anything else. Okay? And that's great news, right? So basically, because we know that, for example, every LP problem can only have a finite number of corner points. Why finite number of corner points? Because, you know, we looked at examples, right? Such as this one, for instance. So if I have a problem with 6 constraints and 3 variables, I can have at most 20 corner points, right? So in the worst case, if I look at each one of them one by one, and if I pick the best one, then I can solve the problem. Okay? And this is really important because the number of points, number of feasible solutions in this cube is infinity, basically, okay? So you have infinitely many feasible solutions, but you have only 8 corner points. So just look at each one of them one by one, and pick the best solution, best with respect to the objective function, and that will be your optimal solution. Okay? So this is really nice, and this is really important. Clearly, this is true for unique optimal solutions. If your LP problem has a unique optimal solution, then that solution should always be a corner point. Okay, so we have seen examples of this before. But this is also true for multiple or alternate optimal solutions. So even if your LP problem has alternate optimal solutions, then there will still be at least one corner point which is optimal. Okay? Now, before we stop, there's one last thing that I want you to be careful about. So please read this statement carefully. So it says that if there is an optimal solution and if there's a corner point, then there's always a corner point which is optimal. So what it doesn't say is the following. It doesn't say that every optimal solution is a corner point. Okay? It doesn't say that. Because, for example, if you look at this example, this point right here is still an optimal solution, but this is not a corner point. Okay? So it tells you that there's at least one corner point which is optimal. Okay? So there may be many optimal solutions, okay? And not every optimal solution is a corner point, but I know that there's at least one corner point which is optimal. Okay? That's important. That's an important distinction. So please do not sort of think that, you know, if there's a solution, then it's always a corner point. Okay? So in general, there may be optimal solutions which are not corner points, but there will be at least one corner point which is optimal. So that's important. Okay? So we'll continue on Thursday.